Hello friends, I Professor Darshan Thakur is going to explain this term mathematical modeling of control system, right? So with the help of this basic example we will try to learn how we are going through this terminology that can be called it as a mathematical modeling of control system, right? So what is the objective for this given system? With the help of this question the objective is very clear key, write the set of equations for following system and draw the force voltage analogous circuit and force current analogous circuit. So one by one we will try to complete these three objective, right? So first objective itself is a answer to the question key, what do you mean by the mathematical modeling of control system, right? So the way in which we are writing the set of system equation from this given mechanical system is nothing but mathematical modeling, right? So in first step what we need to do, first of all we need to understand why this given system falls under the category of mechanical control system, because whether it is mechanical control system or electrical control system, first of all control system is nothing but what? It is an arrangement of different physical elements, those are connected in such a way that to attain a certain objective out of it. That is the basic definition of this control system, right? So from sake of observation we need to observe how many basic elements are connected or associated with this given mechanical system, right? So as you can see there are two masses we are having with us, mass number 1 and this is mass number 2, right? And along with these two masses there are two dampers, or we can say that these are the two friction moments denoted by B1 and B2. Now one question arises in our mind, what this friction stands for, right? So just similar to the in case of electrical circuit, the basic property of this resistor is to oppose the flow of current, am I right? So similarly this mechanical system purely deals with the motion, either it is translation motion or the rotational motion, right? So the factor which will oppose the flow of motion is nothing but what? That can be called it as a damper, or we can call it as a friction, right? So here in this system there are two dampers, B1 and B2. So to each and every damper there are two identical ends. This is the lower end and this is the front end, right? So this lower end is rested towards the ground axis and the front end is associated with this displacement that can be called it as a x1, right? So when we apply, F stands for what? A certain force in this direction. So at that time what will happen as far as this mass number 1 or mass number 2 is concerned, all the particles belongs to this mass number 1 will go through an equal displacement denoted by this x1 in this direction. This direction is similar to the direction of applied force. Similarly, as far as this mass number 2 is concerned, whenever we apply a certain force in this downward direction, so all the particles which are present through this mass number 2 will go through the certain displacement in this downward direction denoted by this x2, right? So similarly this B2 is associated with these two different displacements. The front end of this B2 is associated with x1 and the lower end of this B2 is associated with x2, means it is connected in between x1 and x2, right? Similarly the third element is denoted by this inductor, that is nothing but what? K2. So here K stands for what? The spring. So these three are the basic elements of this mechanical system: mass, this damper and spring. That's why this given control system falls under the category of mechanical system, right? So to write the set of system equation from this given mechanical system, in first step we need to enlist how many physical elements are connected in this system, right? So as a part of this, first of all we need to enlist how many number of masses we are having with us, right? So as I told you earlier, we are having two masses, mass number 1 associated with this displacement x1 and mass number 2 is associated with this displacement number 2 denoted by x2, right? Immediately after that we need to enlist how many number of dampers we are having with us, right? So as we are having two dampers, B1 and B2. Now this B1, as you can see, the lower end of this B1 is connected to the ground axis and the upper end of this B1 is connected to the displacement number 1, and this B2 is associated with this displacement number 2 and displacement number 1. As a result of this B1 belongs to this displacement x1 and this B2 fellow belongs to displacement number 2 and displacement number 1, right? So immediately after that, the third element is nothing but what? This spring. Third element is nothing but this spring, right? This spring is denoted by this K2, right? And this K2, how it is connected in that system? This spring K2 is to that K2, again we are having two different ends. So this is how usually the spring is denoted. To that spring always we are having two ends, A and B, right? When we apply a certain force from left hand side to the right hand side, from A to B, so the net displacement will be A minus B, right? When we apply a certain force from right hand side, so at that time the net displacement will be B minus A, right? So here one end of this spring is associated with this ground axis, right? So overall displacement belongs to this spring number 2, right? The lower end of this spring number 2 is connected to this displacement number 2. As you can see, the upper end of this K2 is connected to ground axis. So this as a result of this spring number 2 K2 is associated with this displacement number 2, right? So in this way we need to enlist the number of elements those are connected in this system. After that, in that step number 2, we need to draw the equivalent nodal diagram, right? So how this equivalent nodal diagram is to be drawn? This nodal diagram is to be drawn from this step number 1, in which we had enlisted the number of different physical elements, right? Okay, so in order to draw this nodal diagram, right, from this given mechanical system, right? This is the given mechanical system. In this given mechanical system, these are the elements those are associated with displacement number 1 or displacement number 2, right? Then in that step number 2, we need to draw the nodal diagram. So in case of nodal diagram, first of all we need to define the number of nodes, right? Without this we cannot complete the nodal diagram. So number of nodes always equals to number of displacement, right? So there are how many displacements we are having in this graphical representation? So as you can see, there are two displacement number 1 and displacement number 2. So the number of nodes always equals to number of displacement. So as a result of this, we need to include the two different nodes. This is the first node associated with x1 and this will be the second node associated with this x2, right? And this lower line represents the ground surface or the ground axis, right? So now in order to complete this nodal diagram, as far as step number 1 is concerned, so this mass number 1 is associated with this displacement x1, right? Why? Because carefully just try to see how this mass number 1 is connected in this nodal is connected in this given mechanical system. One end of this mass is terminated to the reference axis and another end of this mass is associated with this displacement number 1, right? So this m1 is connected in between displacement number 1 and the ground surface, right? Similarly, how this m2 is connected? This m2 is connected in between ground surface and displacement number 2. This damper or friction number 1, how it is connected in this mechanical system? The lower end of this damper is connected to ground axis and the upper end it is being connected to the x1, right? Similarly, this B2, how it is connected? The lower end of B2 is connected towards the x2 and upper end is terminated towards the x1, right? And as far as this spring is concerned, so as I told you earlier, lower end is terminated at ground surface and the upper end is connected towards the displacement number 2, right? So accordingly we need to complete this nodal diagram. So number of nodes equals to number of displacement. So x1 and x2, these are the two displacement, and this horizontal line represents the reference axis or the round axis, right? So first of all we need to include this mass number 1, right? It is represented in this way, right? It is connected between the displacement number 1 and the ground surface, right? Similarly we need to include the mass number 2. This is m2, it is connected in between displacement number 2 and the ground surface, right? Now as far as the dampers are concerned, damper number 1 and damper number 2. So damper number 1 is purely associated with this displacement number 1, right? So how it is being connected in this nodal diagram? This is the damper number 1. This is the usual symbol for this damper. So that can be called it is as a B1, right? What about this B2? Carefully you just try to see in this given system representation, this B2 is associated with x2 and x1, right? Means one end of this B2 is connected to x1 and another end is connected to x2. So in this manner we need to include this damper number 2 in this nodal diagram in this way. See, this will be the damper number 2. One end of this damper is connected to x1 and another end of this damper is connected to x2, right? With respect to the direction of applied force, this is the direction of force, as you can see denoted by F, right? Now this m1 m2 are being taken into account, right? This b1 and b2 is this b1 and b2 are also being taken into account, right? So the remaining element is nothing but what? From step number 1, m1 is connected, m2 is being connected, these two dampers are being also taken into account. So the remaining element is nothing but what? This spring number 2, K2, right? So how this K2 is connected? One end of this K2 is connected to ground axis and another end of this K2 is connected to this displacement number 2. So accordingly we need to convert this or we need to include this K2 in this way. That can be called it is as a K2. One end of this K2 is connected to x2 and another end of this K2 is connected to the ground surface, right? Now as I told you earlier, modeling is nothing but what? The way in which we are or we do can convert this nodal diagram into the equivalent system equation. So here what we need to do, we need to use this strategy that can be called it is as a KCL, right? So KCL stands for Kirchhoff current law, right? So as you can see, we are having two different nodes, x1 and x2. So we need to apply this KCL strategy at node number 1 and node number 2 in terms of forces, right? Because according to this KCL, the sum of incoming plus outgoing currents equals to 0, or sum of incoming currents equals to sum of outgoing currents. So when we apply this KCL at node 1, so at that time what type of system equation we are getting? So basically node is nothing but what? The point at which the multiple number of branches are interconnected to each other, right? So there are how many branches those are being interconnected at this node? This is the first one, right? This will be the second one, this will be the third one, and this will be the fourth one, right? So this is the direction of applied force, this is the direction of natural force at this node number 1, right? The direction of this force is obviously incoming towards this node, right? So we need to assume the direction of this forces belongs to these remaining 3 branches. This will be the first one, this will be the second, and this will be the third, right? So the direction of force or the direction of applied force is incoming to this node. So obviously as far as these 3 branches are concerned, so the direction of force is outgoing from this node, right? So by taking into account this fact, this when we apply this Kirchhoff current law strategy in terms of force at this node number 1, so the system equation will get what? F equals to B1. So when we apply this Kirchhoff current law at this node number 1. So at that time, this is the direction of applied force which is incoming towards this node, right? And as far as these three branches are concerned, one belongs to B1, one belongs to M1, and third one belongs to B2. The direction of force of these three branches are outgoing from this node, right? So Kirchhoff current law says that sum of incoming plus outgoing equals to 0, or sum of incoming currents equals to outgoing currents. Here in terms of force, this will be the incoming force, right? And immediately after that, we need to write the system equation belongs to B1, M1 and B2, right? So as we are very much aware of this thing, this B1 is nothing but what? The first order differentiation, means this B1 itself is a velocity, right? So this B1 is associated with which displacement? X1, right? So accordingly, its system equation will become the first order differentiation with respect to displacement number 1. It will become dx1 by dt, right? Plus the another force belongs to this mass number n will mass number m1 will be what? This m1 followed by, now this mass itself is a, that can be denoted by this term that can be called it as a acceleration. So whenever we apply a certain force, so at that time there will be a certain sort of acceleration through this mass, right, in the direction of applied force. So acceleration itself is a second order differentiation. So as we know how to replace this m1 with this system equation with so the second order differentiation with respect to its displacement will be d square x1 upon dt square, right? Plus the remaining elements, or the remaining third branch associated with this x1 is nothing but in which this damper B2 is being connected, right? So as you can see, this is the direction of applied force. So the direction of force belongs to this branch is outgoing from this node. It will goes from x1 to x2. So the overall displacement through this B2 with the help of this system equation will be what? As I told you earlier, B2 stands for what? Velocity, means first order differentiation. So it will become d x1 minus x2 upon dt, right? So this whole equation that can be treated as a equation number 1, which is nothing but what? The system equation at node number 1. This is the incoming force. This is the system equation belongs to damper, first order differentiation, velocity. This is the system equation belongs to mass, second order differentiation, and this is the system equation belongs to the damper number 2, that is nothing but what? B2, as it is connected in between x1 and x2. So the overall displacement will become d x1 minus x2 by dt, right? Now similarly, when we apply this Kirchhoff current law at node number 2, right, at node number 2. So at this node, see, at this node there are how many branches are interconnected to each other? This is the first one, right? This will be the second one, and this will be the third one. This is the direction of force, which is by default the nature of that force is incoming, because it is going from x1 to x2, means it is incoming towards the x2, and the direction of these two forces belongs to m2 and k2 are outgoing from this node, right? So in order to write the system equation, as there are three branches, out of that three branches, this branch is nothing but what? Incoming, and the remaining two branches are outgoing from this node, right? So one more time, the system equation belongs to this B2 is nothing but what? How to map this B2 with respect to system equation? Damper stands for velocity, first order differentiation. So it will become dx1 minus x2 by dt equals to, how that mass is being mapped in terms of system equation, as it is mass number 2, so it is a second order differentiation, acceleration, right? So d square x2 upon dt square. In this way, this mass number 2 is being taken into account, plus, right, this k2 followed by the desired displacement, that is nothing but what? x2, right? So this will be the system equation number 2, right? This is equation number 1. When we apply this KCL at node number 1, right? When we apply this KCL at node number 1, so there are 4 branches, those are being interconnected to this node number 1. Out of that 4, this is the direction of applied force, and the remaining 3 branches are the direction of force of these 3 branches are outgoing from this node, in which we are having this B1, we are having this M1, and we are having this B2. Similarly, when we apply this KCL at node number 2, so at that time there are 3 branches, those are being interconnected at this node. So the system equations of these 3 branches are, the force belongs to this branch is incoming to this node, so its system equation will become B2 times of dx1 minus x2, because it is connected in between x1 and x2. The system equation for this mass number 2, whenever that mass is being taken into account, so this second order differentiation is, we need to consider the second order differentiation, so it will become d square x2 upon dt square plus k2 times of x2, right? One end of that spring is connected to the reference axis, so the overall displacement will be what? x2 itself is the overall displacement. So in this way the system equations are to be right. So after declaring these two system equations from this nodal equivalent diagram, next thing what we need to do here is, we need to draw the force voltage analogous circuit, right? So force voltage analogous circuit means we need to recall what are the analogous terms belongs to this force voltage analogy, right? So as far as these analogous terms are concerned, so this force is analogous to voltage in this analogy. Similarly, this M is analogous to L. Damper, as I told you earlier, what is the functionality of the damper? It will have tendency to oppose the flow of motion, denoted by B. So in case of electrical engineering, which fellow is responsible to oppose the flow of current? That is nothing but what? R. So this B is being replaced by R. Similarly, the third element is nothing but what? Spring. So this spring is nothing but what? Elasticity. So which is to be denoted by 1 over C, stands for elasticity or the deformation force, right? So again, one more important thing here, I is analogous to Q, current is analogous to charge, right? So in order to draw the force voltage analogous circuit, what we need to do as far as these two equations are concerned, so we need to rewrite these two equations in terms of force voltage analogy, right? So as we know, equation number 1 is written for F, right? So this F will become V, right? Because this force, right, is analogous to voltage. As a result of this F is analogous to V. Then this damper is analogous to R. So this B1 will become R1, right? Followed by dx1 by dt, right? So here, as I told you earlier, this x stands for what? This x is nothing but what? This x is nothing but displacement, right? So here this x is being replaced by q, that is nothing but what? Charge. So as a result of doing this, it will become d q1 by dt plus, again this M is analogous to L, so it will become L1 into d square, this x1 is analogous to q1, d square q1 upon dt square plus this B is nothing but what? R. So R2 into d q1 minus q2 divided by dt, right? Moreover, when we apply the Laplace transform, right, to this equation number 1, because this is the time domain representation, so when we apply the Laplace transform, this time domain representation is converted into frequency domain representation or the S domain representation, right? So as a result of this, our equation number 1 will become this f of s equals to, or as a result of force voltage analogy, this force is nothing but what? Voltage. So it will become V of s equals to r1 into, right, r1 into, as it is the first order differentiation, so the Laplace variable for first order differentiation will be what, capital S into q1 of s, right, plus this L1 into, this is the second order differentiation, so Laplace variable will be s square, L1 s square into q1 of s, right, plus r2 into s times of q1 of s minus q2 of s, right. So this will become the equation number 3, right. So what kind of manipulations are to be done in this equation number 1? This equation number 1 is nothing but time domain representation, which is to be declared from this nodal equivalent diagram, right. Then after that, what we need to do, we need to draw the force voltage analogous circuit. So these are the analogous terms which we had discussed already. F is V, M is analogous to L, B is analogous to R, K is analogous to 1 over C. This displacement is analogous to charge, that is nothing but what, Q. So as a result of this, when we apply the Laplace transform to this equation number, or to this existing equation, we are getting this equation, right, equation number 3. Similarly, when we apply the force voltage analogy along with this Laplace transform to this equation number 2, so this equation number 2 will become what, this B is analogous to R. So it will become R2 into, here I will write this equation as it is in terms of time domain. It will become R2 followed by D Q1 minus Q2 upon dt, right. It will become R2 into dq1 minus q2 upon dt from this equation number 2 equals to, right, this m is analogous to which term, this m is analogous to L, so it will become L2, right, followed by, this is the second order differentiation, this x is being analogous to, x is analogous to q. Similarly, this k elasticity is analogous to 1 over c. So our this equation number 2 will become, according to the force voltage analogy, this m2 is being replaced by L2, and as it is the second order differentiation, x is being replaced by q, so it will become d square q upon dt square, plus k is replaced by 1 over c, so it is k2, so it will become 1 over c2 into x2, so x is nothing but what, q2. And when we apply the Laplace transform to this existing equation, so it will become what, this R2 followed by, this is the first order differentiation, so the Laplace variable for first order differentiation, it will become s, so R2s into q1 of s minus q2 of s equals to this L2 times of s square, as it is the second order differentiation, s square into which q we need to consider here, because this L2 means this m is analogous to L, right. So when we consider the equation number 2 here the mass number 2 we are having with us, so this m is analogous to L. So as we are having the mass number 2, so this mass number 2 is replaced by this L2, and this mass number 2 is associated with this displacement number 2 x2, which is being replaced by q2, so it will become L2 s square into q2 of s, right, plus it is 1 over, when we apply the Laplace transform, so it will become 1 over c2s into q2 of s. So this is equation number 4, right. So this is equation number 3 and equation number 4. Now as far as these two equations are concerned, so in this equation what we need to do, this term, which term, s into q of s is being replaced by I of s according to the force voltage analogy. S into q of s is nothing but what, I of s. So accordingly equation number 3 will become what, v of s equals to S into Q of S is being replaced by I of S. So it will become R1, it is S into Q1 of S. So it will become S into Q of S is nothing but I of S. So which I? It will become I1 of S, right? Plus the next term will become what here? Plus L1 into S times of S into Q of S is nothing but what? I of S. So L1 S times of I1 of S, right? Plus the remaining term is what? R2S into Q1 of S minus Q2 of S, where S into Q of S is nothing but I of S. So it will become R2 into I1 of S minus I2 of S, right? So this is how this equation number 3 is being rewritten in this form, right? That can be denoted as a equation number capital A, right? And in same manner, when we replace this term S into Q of S equals to I of S in this equation number 4, so this equation will become what here? Here S into Q of S is nothing but what? I of S. So this equation will become R2 into I1 of S minus I2 of S equals to S into Q2 of S is nothing but I of S. So it will become L2 into S times of I2 of S, because it is S into Q2 of S, plus it is 1 over C2 into, sorry, here we don't have this S term, sorry, so it will become 1 over C2 S into I2 of S. This will be the equation number capital B, right? So this is capital A and this is capital B. So from these two equations we need to draw the force voltage analogous circuit. What we need to do? We need to draw the force voltage analogous circuit. So in order to draw this force voltage analogous circuit, when we carefully observe the equation number capital A and capital B. So equation number 1 is being written for which quantity? Voltage. V of S equals to R1 into I1 of S plus L1 S into I1 of S plus R2 into I1 of S minus I2 of S, right? So as far as these three terms are concerned, R1, L1 and R2. So carefully just try to see the coefficients of these three terms. The coefficient of R1 is I1, the coefficient of L1 is I1, and the coefficient of I2 is nothing but what? I1 minus I2, right? So as these two are the similar coefficients as far as first two terms are concerned, I1 and I1 belongs to R1 and L1, right? Means obviously the similar current flow through this R1 as well as L1. Which current flow through this R1 and L1? The fundamental current, that is nothing but what? I1. Means these two components are obviously connected in series form, right? As far as this remaining term or element is concerned, so the coefficient of this term is I1 minus I2. Means there will be a circulation of I1 as well as I2 through this R2, right? Means we are coming on to this conclusion ki when we draw the force voltage analogous circuit, so at that time, see, this V is nothing but what? The applied voltage, right? So the force voltage analogous circuit will become this is nothing but what? This is the symbol of voltage, that is nothing but what? V, and this is R1, right? And this is L1, right? R1 and L1, because the coefficient of R1 is I1 and the coefficient of L1 is also I1, but the coefficient of R2 is I1 as well as I2. So in this way, this is nothing but what? R2, right? From this equation number capital A. As far as equation number capital B is concerned, so what is written to the left hand side of this assignment operator? The coefficient is R2 times of I1 minus I2. So already it is being taken into account. And as far as these two terms are concerned, L2 and 1 over C2, right? So what are the coefficients of these two terms? The coefficient of L2 is I2 and the coefficient of 1 over C2 is also I2. Means the same current flow through this L2 as well as 1 over C2. That is nothing but what? Elasticity, or in graphical manner we can call it as a C2, right? So there will be a circulation of I2 through this L2 as well as C2. So that's why these two components are connected in series form, right? So this will be L2, right, and this will be the C2. So in this way the force voltage analogous circuit is to be drawn. This is the first fundamental current I1, and this is second fundamental current I2, and this is the which component? C2. So there will be a circulation of I1 through this R1 and L1 according to this equation number A. The coefficient of R1 is I1 and the coefficient of L1 is also I1, means this current flow through this R1 and L1. As far as the equation number capital B is concerned, so the right hand side of this equation number left hand side of this equation number capital B is nothing but R2 times of I1 minus I2, means through this resistor I2 there will be a circulation of I1 as well as I2. That's why it is being connected in shunt form as compared to R1 L1 and L2 C2. And as far as L2 C2s are concerned, so there will be a circulation of this fundamental current that can be called it as a I2 through this L2 as well as C2. So this is all about force voltage analogy. Okay, so in case of force current analogy, just similar to the previous one, that is nothing but force voltage analogy. Here we need to declare the analogous term belongs to this force current analogy. So as its name indicate, it is a force current analogy, means this force is analogous to current, right? As we know, this damper, mass and this spring, these are the three important parameters of this mechanical system, which is shown in this nodal diagram. So what we need to do in case of this force current analogy, as this force is analogous to current, similarly this mass is in case of force current analogy, this mass is analogous to C, right? Similarly, the next physical parameter in case of this mechanical system is nothing but this damper, which is denoted by B, right? So this B is analogous to 1 over R in case of force current analogy. And the third important element is nothing but spring, K. So this K is analogous to 1 over L, that is nothing but inductance, right? And the way in which we had replaced in case of force voltage analogy, this displacement is being replaced by Q, right? X is analogous to Q. Similarly, in case of force current analogy, this X is replaced by the flux linkage, that is nothing but psi, right? So these are the analogous terms that we need to remember. By using this analogous term, first of all we need to replace these two equations, equation number 1 and equation number 2, which are being declared as when we apply the Kirchhoff current analogy at node number 1 and at node number 2. So immediately here equation number 1 become, according to force current analogy, this force is no more with us, this F is being replaced by I. So I equals to first parameter, here we are having this damper number 1 B. So here B is nothing but 1 over R. So it is 1 over R into D. X is being replaced by the desired flux linkage, that is nothing but psi. So it will become d psi by dt plus M1. Before going for this M1, this M is nothing but analogous to C, so it will become C1 into d square psi 1 upon dt square plus B2 is nothing but 1 over R2 into d psi 1 minus psi 2 upon dt, right? So in this way this equation will become like this, so that can be called as the equation number capital C. Similarly, we need to rewrite this equation number 2 in by accordingly this force current analogy. So first this equation start with this term which is written to the left hand side of this assignment operator. So initially which element we are having here? B2. So in case of force current analogy, B is nothing but 1 over R. So it will become 1 over R2 into d of psi 1 minus psi 2 upon dt equals to m. M is nothing but C. So C2 into d square, this x is being replaced by flux linkage psi 2. So d square psi 2 upon dt square plus k. Here k is replaced by 1 over L. So it is k2. So 1 by L2 into x is being replaced by psi. So it will become psi 2. So this will become equation number capital D. Right. Then immediately after that, when we apply this Laplace transform to equation number capital C and equation number capital D to convert this time domain expression into the frequency domain expression. So as a result of doing this, it will become I of S equals to 1 over R, as it is a first order differentiation. So the Laplace variable will be S. So S into psi of S plus C1 into S square into psi 1 of S plus R2 into, again one more time, it is a first order derivation. So Laplace variable will be 1 over R2 into S psi 1 of S minus psi 2 of S. So this is how your equation will become. Which equation? Equation number C, when we apply the Laplace transform. So when we apply Laplace transform to equation number capital D, as a result of applying this transform, this equation will become 1 over R2, and it is a first order differentiation. So the Laplace variable will be capital S into psi 1 of S minus psi 2 of S equals to C2 into D square, means S square into psi 2 of S plus here 1 over L2 time of S into psi 2 of S, right? No, we don't have this S coefficient here. 1 over L2 into psi 2 of S, right? Because this is the constant term. Then after that, to draw the force analogous equivalent circuit, one more assumption here we need to do. That assumption is nothing but what? As far as these two equations are concerned, that can be called it as equation number capital E, and if suppose this is equation number capital F, right? So we need to replace this term, which term? S into psi of S equals to V of S. In which two equation? In equation number capital E and equation number capital F, right? So as a result of replacement, this equation number E and equation number F will become what here? First we will consider equation number capital E. So it is written for I of S equals to 1 over R1. This S into psi of S is being replaced by V of S, right? So basically it is first displacement flux linkage constant. So it will become 1 over R1 into S into psi 1 of S, right? So S into psi 1 of S, that can be replaced by V1 of S plus C1 times of, here the coefficient of C1 is S square into psi 1 of S, right? Where S into psi 1 of S is being replaced by V1 of S. So it will become C1 times of S into V1 of S, right? Plus again S into psi of S, that can be treated as a V of S. So it will become 1 over R2 into V1 of S minus V2 of S, right? So this is how equation E can be replaced with this term. Similarly, equation number capital F will become, as a result of replacement, S into psi of S equals to V of S. So this equation begins with this term, which is written to the left hand side of this assignment operator. So it will become 1 over R2 into S into psi of S. So it will become V1 of S minus V2 of S equals to C2 into S square times of psi 2 of S. So it will become C2S into V2 of S, because S into psi of S equals to V of S, plus it is 1 over L2 into psi 2 of S, right, where V of S is nothing but S into psi of S. So we don't have this S term here, so it will obviously become 1 over L2 S into V2 of S, right. So this is how these two equations will become. So now it is very easy for we people to draw the force analogous equivalent circuit from these two equations, right. Carefully when we see these two equations, so as far as this first equation is concerned, which is written for this I of S equals to 1 over R1 into V1 of S plus C1 S times of V1 of S plus 1 over R2 into V1 of S minus V2 of S. Carefully just try to see the coefficients of this term. The coefficient of 1 over R1 is nothing but V1 of S. The coefficient of C1 is nothing but what here? S times of V1 of S. Means this V1 of S is a common term. Means there will be a same voltage across this 1 over R1 as well as across this C1. Similarly, when we carefully try to see the next equation in which the coefficients of this C2 and 1 over L2 are the same. The coefficient for C2 and 1 over L2 is nothing but what? V2 of S, means the same potential difference across C2 as well as across 1 over L2, right. Now if the voltage is same, right, means these two elements are connected in shunt form, right. So as a result of this, definitely we too can convert these two equations into its equivalent electrical circuit. So as a result of doing this, first component that we need to consider this I, right. So basically I is nothing but what? This is the current, so denoted by this symbol I. Immediately after that, the coefficient of R1 and C1 is same, that is nothing but V, means these two elements are connected in shunt form so that they are sharing the similar voltage. If they are sharing the similar current, so these two elements are connected in series form, but here they are sharing the similar voltage, means they are connected in shunt form, right. So this will be R1, we can say that, and this is nothing but what? C1, right. Then as far as this element is concerned, which is nothing but R2, right. So the coefficient of R2 is V1 minus V2, means what? This R2 is connected in what we can say, this fundamental component R2, across this R2 there will be a potential of V1 as well as V2, right. So it is connected in this way. This will be your R2. It is a part of first terminal voltage as well as second terminal voltage, that is nothing but what? R2. And as far as this remaining equation is concerned, so the same term is there to the left hand side of this assignment operator. To the right hand side of this assignment operator, we are having C2 and L2. The coefficient of C2 and L2, they are sharing the similar voltage, means they are connected in shunt form. So this is nothing but your C2, and in that next branch, that will be your L2, right. So as compared to R1 C1 and C2 L2, the coefficient of 1 over R2 is nothing but V1 as well as V2, right. So this is V1, this is V2, that's why it is being connected in this way. So this is nothing but what? The force current analogous circuit, right. So these three are the objectives of these three numerical, right. First we had in that first objective we had declared the system equation, right. We had declared the system equation by converting this mechanical system into its equivalent nodal diagram, right. In the second objective is what? That is nothing but force voltage analogous circuit. And third objective is nothing but what? Which we had completed here, that is force current analogous circuit. So in this way, this all terminology related to mathematical modeling, right? Mathematical modeling of this control system. So in order to replace this given control system with the help of system equations, that is to be done with this terminology that can be called it as a modeling, right? So this is how mathematical modeling is to be done. Okay, thank you.